Welcome to the office. We want to continue taking a look at direct products and finitely generated abelian groups. Now that we've talked about our main theorem for the section, what we'd like to do is we'd like to take a look at some applications of that theorem. Now, the reality is that the applications of that theorem are just other theorems which are proven using that theorem. In order for us to talk about those theorems, at least one of them talks about the idea of decomposable, so a group being decomposable. What we'd like to do is we'd like to take a look at what it means to be decomposable, and then an example of a group that is indeed decomposable. All right, so a group G is decomposable if it is isomorphic to a direct product of two or more proper non-trivial subgroups of itself. Otherwise, G is indecomposable. All right, so let's consider in S7, we have the element sigma and the element tau. And of course, these elements are functions. These functions are permutations, and we can, they're both cycles, so very nicely in cycle notation there. The subgroups that generated by sigma and that generated by let's see here. I made a error there. The subgroups generated by sigma and tau. Tau, not sigma again. So my apologies. These are subgroups of the group generated by sigma and tau together. So we have this subgroup of S7, which we can think of as a group itself, right? Every subgroup is a group. So we have this group generated by sigma and tau. What I would like to do is I would like to recognize, again, that same copy error here. What I'd like to recognize is that the subgroup generated by sigma and tau, or the group generated by sigma and tau, is isomorphic to the cross product, or the direct product rather, of the subgroup generated by sigma and the subgroup generated by tau. Of course, these subgroups are subgroups of this. And so this feels a little bit weird, of course, because I'm generating something, and then and so it seems like I'm trivializing this or making a very contrived example. Oh, it only works in special circumstances, and yeah, that's technically true. Or you might think to yourself, well, gosh, can't you just take what's generated by any two elements and then look at those two individually as well? So, like, if I wanted to consider S6, I could say, well, let's look at row 1 and mu1, right? What's generated by these two in S3. Maybe I said S6, I don't know. I meant S3, right? Those isometries of a triangle. So here in S3 itself is not generated, well, it can be generated by row 1 and mu1. However, it is not a direct product of row 1 and mu1. And the reason that it's not is in part because it lacks commutativity. So what I've done is, yes, I've chosen an example that seems to be very simple, and it is, but only because I chose special circumstances in which sigma and tau commute. So we have something that is abelian. So abelian is the most basic or the easiest case to handle. So again, where are we at? What have we got going on? Look, sigma, tau, they can generate subgroups generated by sigma, generated by tau. We can also consider together the subgroup generated by sigma and tau. Clearly, the individual is not the same as the collective. So how do they relate? It actually works out that because of the commutativity, we can express this as the direct product of that. And you might say, how do we know it's isomorphic? All right, let's take a isomorphism. Let's create an isomorphism. I'm not going to go through all the justification, but I do want to at least present the idea here. So I want to go from what's generated by sigma and tau together to the direct product of what's generated by sigma product with what's generated by tau. And I can do that by taking, well, actually by noticing for some element, let's call it, so let's see here. Oh, let's just call it P for permutation. So for some permutation that belongs to what's generated by sigma and tau, that permutation P may be written as sigma to a power times tau to a power. And the reason that we have that is because they commute. So any collection of products, I can rearrange them. So it's just sigma to a power, tau to a power. Then define phi of P to be phi of sigma to the n, tau to the m. And we can consider this to be, since we're taking things that belong in here, cross product with things that belong in here, I would say sigma to the n, tau to the m. And of course, it's pretty clear that this belongs in there and this belongs in here because that's what's generated by those. And that's what's generated by that. Okay. Yeah, this, right. This contains all the powers of sigma. This contains all the powers of tau. Hey, look, it's just a power of sigma and a power of tau. Excellent. So we know that it belongs there. And indeed, we can say that this is an isomorphism. So it can be shown that this is an isomorphism. I'm not going to work through all of the details right now. That's just not what I'm interested in. What I'm interested in is simply observing that what we have is that this group here is decomposable because it can be expressed as the direct product of two of its subgroups. As simple as that, okay? All right, that's all that I wanted to share for now. So thank you for your time and attention. Join me back here again for more on direct products and finitely generated abelian groups.